Okay, so let us start. All right, so we are almost towards the end of the semester and end of the course as well. Yeah, so today I will finish theory behind sampling and we will start looking at some problems also, one or two. Uh, so NSEM exam is, by the way, I don't know, I have not seen the schedule yet. I don't know whether it is out or not. So yeah, if any one of you know, then yeah, let all of us know. Okay. If if I come to know about it, I will also inform you guys. But so far, I have not heard anything when it is scheduled and so on. But most likely, it's going to be, uh, I think, on 20th because 19th is a holiday, and yeah, 20th is the last date. And so our Friday's class, yes, that slot I suspect is what we have on the Saturday of next week. But yeah, that is what I suspect. Okay, I have not heard it officially yet. So this week we will have regular classes, four of them, and yeah, next week, yeah, what I suspect is we will have classes on Thursday and Wednesday, and yeah, Friday's class or whatever. If it had not been a holiday, we would have had a test on that day. But yeah, since it is a holiday now, uh, it will be on Saturday, I suspect. All right, so yeah, let us continue our discussion about sampling here. So we went through this thing, not from the type notes, but yeah, we did it on Jamboard last week. So given a continuous signal which is band limited, so band limited means frequency spectrum is non-zero only over a finite interval. Okay, so for example, from minus omega m to plus omega m. That, that's what we mean by band limited, and we saw band limited, time limited, how they are related to one another. So sampling theorem applies only for band limited signal. Okay, so yeah, the corresponding time signal must be time unlimited. If you have a time limited signal, then yeah, exact reconstruction is not possible with any sampling rate, but you can still get close enough approximations. Okay, with large enough sampling rate and so forth. Okay, but for band limited, yeah, in theory you can get an exact reconstruction. So we used the multiplication convolution property. Uh, so when you sample in time domain, that corresponds to multiplication with impulse train in time domain. And in the frequency domain, we have convolution with the frequency spectrum with again a train of impulses. And if you have a compressed train of impulses in time domain, that means the sampling rate is high. You have close enough impulses in time domain, then uh, its Fourier transform will be spread out in the frequency domain. And, that's the idea behind sampling theorem. If this train of impulses is spread out, then yeah, these spectra are not going to overlap with one another. On the other hand, if you have a spread out train of impulses in time domain, then you will get a compressed train in the frequency domain. In that case, there will be overlap and you cannot have exact recovery. Okay. So we saw last time that yeah, this first shifted spectra, how to ensure that that does not overlap with the original spectra. So minus omega m to plus omega m, and the bandwidth of this first shifted spectra is from omega s minus omega m to omega s plus omega m. The right hand lobe ends at omega s plus omega m, this one. And, yeah, this is this one. So omega m, this the point where the principal lobe terminates, yeah, that must be to the left of the point where the redundant mode starts. Omega s minus omega m, that is this point that must be to the right of omega m. So this is the idea behind sampling theorem, and provided that this criteria is satisfied, you get exact recovery. Okay, let me see the comment. Okay. All right. So any questions on that? Okay. So let us continue further. So let's look at the phenomenon of aliasing. So I will explain what do we mean by alias with this example. Some of you might have already heard this term. Okay. So alias is something. So calling someone by a different name. Okay, that's what it means by this term alias. So yeah, you may have two names for the same entity, for example. The alternate one can be treated as an alias. So we will see how this relates to sampling and reconstruction. Okay, so let's start with a cosine wave. This is our signal, cos of omega mt. So we have just one fundamental frequency. So when we take its Fourier transform, you are going to get these two uh, impulses. Yeah. So e to the power j omega mt plus e to the power minus j omega mt over 2. And, yeah, those exponentials are going to give these shifted impulses in frequency domain. Okay. So this omega naught, by the way, is same as omega m. I hope you can see this. Maybe I can increase the size a bit. Okay. So this is the Fourier transform, the first picture of the time domain signal. Let me also draw it in time domain. I have a sine function like this. Start. Okay. So this is a train of impulse. I think I have here also. Yeah. So the period is t. Okay, in time domain. And, yeah, this is cosine function in time domain. And now in the frequency domain, yeah, cosine can be represented by these two impulses at plus and minus omega naught or plus and minus omega m. Okay. So let's take Fourier transform of this impulse train also. In the frequency domain, you are going to have uh, Dirac delta at integer multiples of omega s. Omega s is 2 pi over t. So multiplication is going to turn into convolution in the frequency domain. So we had a multiplication in time domain, and we are going to have convolution in the frequency domain. Okay. So this omega naught is going to get convolved with Dirac delta at the origin and give us the same impulse at omega naught, and likewise for this minus omega naught. Okay. So these two impulses, when convolved with this impulse at the origin, that's going to give us these two impulses. I hope that is fine with everyone. see any questions. Okay, so the impulse at the origin is taken care of. Okay, impulse at the origin of the train of impulses. So this is train of impulses in the time domain. This is in the frequency domain, and we have convolved this impulse at the origin with these two impulses. That gave us these two impulses. Now let's take this one and this one by one. Okay. So now these two, when convolved with say this impulse, they are going to give us these two shifted impulses. Yeah, omega naught plus omega s and omega s minus omega naught. Okay, when convolved with this Dirac impulse, yeah, that's going to give us these two impulses, and likewise these two for this impulse at minus omega naught, minus omega s. Okay, so that's how yeah, these three pairs are obtained. First pair is obtained by convolving this with the impulse at the origin, and the other two by convolving the impulses at plus and minus omega h. And likewise, you will get more pairs, okay, corresponding to impulses at integer multiples of omega s. All right. So the underlying assumption here is omega s minus omega naught is bigger than omega naught. Okay, so we are assuming that the Nyquist criteria is satisfied. That's why, yeah, there are no overlaps. Okay, so in the picture below also, for example, yeah, in this picture. Okay, so before going to that, let us concentrate on this picture. So provided that Nyquist criterion is satisfied, that is omega s is strictly bigger than 2 times omega naught or 2 times omega m. If we use a low pass filter of bandwidth minus omega s over 2 and plus omega s over 2, then we can perfectly reconstruct the original cosine signal. Okay. Because we have avoided any sort of overlap. Alright, so let's start reducing our sampling rate slowly. So for example, in here, omega naught, which is this one, is 2 over 6 times omega s. So 3 times omega naught is, let us see first here, what is the sampling rate. So in this example, they have considered the case where omega naught is omega s over 6. So omega s is 6 times omega naught. Okay, so maybe I will write that omega s is 6 times omega naught. We only need 2 times omega naught to get exact recovery. Yeah. So 6 times, of course, is going to give us exact recovery. That's why we see that the recovery works perfectly here. In the second case, we have 6 times omega naught is equal to 2 times omega s. So let's also write that. So this is the first case. Second one. So that is 3 times omega naught is omega s. I hope this is correct. Yes, omega s is 3 times omega naught. So again, Nyquist criterion is satisfied. We want omega s to be strictly bigger than omega naught. So here also you see this harmonic I don't know whether it is correct to call it harmonic or not, but yeah, just for the sake of it, I'm calling this harmonic or whatever, this subband. It's coming closer to the original spectra, but yeah, they are still separated. Okay, so again, if you use the same low pass filter of frequency omega s over 2 plus or minus omega s over 2, you can recover your original cosine signal perfectly, because this is still not interfering with the primary signal. So now let's reduce the sampling frequency further. Okay. And now here we see an alias. So now let's look at the sampling rate. It is 2/3 omega naught now. Okay. So omega s is 3 over 2 times omega naught. So let's correct that. Omega. So Nyquist criteria is not satisfied. And let us see what happens in here. So we had these two impulses at plus and minus omega naught. So okay, we are in this picture. So here it is at omega naught, and this dotted one at minus omega naught. Okay, the first shifted one was at omega s minus omega naught. So let's see what is omega s minus omega naught. So in this case, it turns out to be let us see 1.5 times omega naught minus omega naught. So this is zero point 0.5 omega naught. Omega s is 1.5 times omega naught, and we are subtracting omega naught. So zero point 0.5 omega naught clearly lies to the left of omega naught, right? So that's why this this impulse it was to the right of this when the Nyquist criteria was satisfied. When it is not satisfied, comes to the left of this primary impulse, and likewise here also. Yeah, this one, which was to the left of this impulse. When Nyquist criteria gets violated, this comes to the right of this. Okay, like that. And now if you uh, take a low pass filter of cutoff frequency plus and minus omega s over 2, instead of getting your primary signal, yeah, this alias gets picked up. Okay, so when you apply the low pass filter with this cutoff, then what you recover is a continuous time signal with cosine signal with frequency omega s minus omega naught. Okay, so instead of getting your signal of frequency omega naught or omega m, you end up getting a signal of frequency omega s minus omega naught. Okay. And likewise, if you take any other sampling rate which does not satisfy Nyquist criteria, you are going to get some pseudo signal instead of your original signal, and that is what we mean by alias. Okay. So, any questions on that? I hope.
Sir, is it just occurs? Will it just occur, or is there any purpose to make that aliasing?
Please repeat your question.
Sir, is there any purpose? I mean, will we ever do aliasing purposefully?
Okay, so you would want to avoid alias if you want to have perfect recovery. Yeah, so we are studying alias because yeah, we want to understand what happens if the Nyquist criteria gets violated, and if we are looking for an exact recovery from discrete samples, then we would like to avoid this alias. Okay, and to avoid aliasing, we must satisfy Nyquist sampling theorem. the criteria of Nyquist theorem. If it gets violated, then you end up having aliasing. Okay, so that's what I was explaining.
Okay.
So we would want to avoid this, okay, in general, yeah, for having perfect recovery. If yeah, if you have an alias, then yeah, you cannot recover your original signal, and you can also understand this from another picture. So if you have some discrete impulses like that, so I'll draw them spread out. Then you can fit more than one signals. Okay, when sampled with these impulse train first. I can also take a picture like this. Maybe it is oscillating like this. So there are more than one signals which can give you same samples. Okay, like that, and yeah, you can draw more than one, more than two. I'm sorry. Maybe one of them I will draw in dark and then one will draw that. Okay, so this is not a one-to-one mapping in general, going from continuous time domain to discrete time domain. Yeah. But when you know what is your underlying continuous time signal, and when you sample it, then we are asking the question: can you get back the continuous time signal? Yeah. So if you know to start with what is your continuous time signal, then you also know its frequency spectrum, and yeah, then you can see if the Nyquist criteria is getting satisfied or violated, and from that you can know whether the perfect recovery is possible or not of your original signal. But if you are just given some discrete samples, then of course there could be multiple continuous time signals associated with that. Yeah, and when Nyquist criteria gets violated, then yeah, any one of these possible signals you can pick up when you do the low pass filtering. I hope.
Yes.
Uh, yes, someone had a question. I think. Okay, so continue. Yeah, so you need to play with this a bit to get more better understanding of what what is really happening in here. But yes, I hope you have had at least some idea. Uh, so someone is not on mute, so yeah, please mute yourself if you don't want to ask any question. Okay, so that is sampling and recovery with low pass filtering. But yes, there are some specific cases where we can use band pass filtering also to get a perfect recovery. Okay. For example, yeah, let me take you through this itself. So suppose again we have a band limited signal, for example, in the interval omega 1 and omega 2. So something like this. Okay, so this is in the frequency domain. Now when you associated with some continuous time signal, and now when you sample it, you're going to get something like this, okay, periodic repetitions. So this is after sampling. And now, if you want to reconstruct your original signal, then you need not take low pass filter of frequency 2 times omega 2. Okay, you can just take a low band pass filter which has bandwidth omega 2 minus omega 1. And, you can still recover your original signal. Okay, so even without satisfying Nyquist criteria, you can recover such signals, okay, which have finite bandwidth like this over some limited range. So this I have drawn it quite badly actually. So suppose we are given a frequency spectrum like this, then if we sample with a frequency which is 2 times omega 2, then okay, you are not going to have anything in here. Starting at minus omega 1 and minus omega 2, you will get first shift and so forth. Okay, that is given that omega s is strictly bigger than omega 2. But you don't need omega s to be strictly bigger than twice omega 2. Even with low sampling frequency, you can still get a perfect recovery by using bandpass filtering. I don't know whether I explained that clearly, but yes, if there is any question or yeah, confusion, please let me know. I can explain this again. You can just go through this paragraph. Okay, should be understandable. We don't need sampling of 2 times omega 2. Okay, even with lower sampling rate, you just need to ensure that this shifted spectra, they don't overlap with one another. Okay, and they won't overlap provided your omega s. So let me write that here. Omega s is bigger than omega 2 minus omega 1. So yeah, first low here, this will be omega omega. Yeah, the one here will also be something. Let me not get into create a confusion. Okay, so just go through this and yeah, if it is still not clear, we can discuss this again tomorrow or on Friday's class, or even we have 2 classes next week also. So that is the band pass sampling, and maybe we can look at examples now so that it will become more clear what is it that we are doing. Yes, any questions? I will just wait for.
Yes, sir.
Yeah, please go ahead.
Sir, in real life, how will we avoid this aliasing? Is there a like universal agreement on what frequency signals are received or something?
No, no. Okay. So if you know your continuous time signal, and if you know its bandwidth also, so okay, let me write that. So we are given some continuous time signal, which is band limited. Band L, let me write. So for such signals, we want to ask the question: can we avoid aliasing?
No, sir. Sir, I understand we can avoid aliasing, but
Okay. Yes,
so
yes.
the place where the signal is received, do we already have the information of what frequency signal we want to reconstruct? Because
Yes, yes. So that information, yes, you need to have, because yes, you want to reconstruct exactly the signal which has been transmitted, and unless that information is not known at the receiver, at least the bandwidth and fundamental frequency, uh, you cannot have exact recovery, because the
okay.
yeah, go ahead.
No, sir, I understand.
So let me just say it one more time. So you are given some signal having bandwidth, maybe this omega m2 plus omega m. So that information is known at the transmitter, and receiver also must know that. Okay, the spectra lies within this this bandwidth, and now with that information, it needs to reconstruct the original waveform exactly. Okay, so receiver assumes that the Nyquist criteria is satisfied, and then it will use a low pass filter, okay, of a bandwidth which is strictly bigger than twice omega m. So low pass filter with cutoff 2 times omega m. This using this, the receiver can reconstruct the original signal. Okay, but if the transmitter uh, itself violates Nyquist criteria, then okay, receiver assumes that yeah, you have your frequency spectra within this interval, and then when it tries to apply the low pass filter, the receiver ends up having aliasing. Okay, so Nyquist criteria is satisfied by the transmitter, receiver cannot have exact recovery, even though receiver knows about the bandwidth of the original signal. So aliasing at the receiver end, transmitter must satisfy Nyquist type sampling criteria. Then it transmits information about this bandwidth, etc., to the receiver, and okay, then the receiver just applies the low pass filter with appropriate cutoff, and yeah, gets exact. Is that clear, or did I confuse you?
Yes, sir. My only question was we need to know the information at the receiver side, and we answer is yes.
Yes, and the transmitter also must satisfy Nyquist sampling criteria, so
Yes,
that
sir.
receiver does not get any alias. Yes, so those two things, yes, are important. Yeah, this is a subtle point. So yeah, there are any questions? Yes, please let me know. Okay, so let us continue. So let's look at this example. So I will explain the example first. So this bandpass sampling we will encounter in here. Yeah, I'm getting some noise, so yeah, if there is any question, otherwise I'll mute this one. Okay, so if you have not understood bandpass sampling properly from yeah, what I just said, yeah, maybe this example will give a better clue. So this is a frequency spectrum of some continuous time signal. So it has these two bands over plus and minus omega 1 and omega 2, and we are sampling this in time domain. Okay, so this is the continuous time signal. This is a train of impulses, that. I think we have that. So this is the train of impulses in time domain. And then the sample signal is passed through some filter, and we want to ask, can we have a perfect recovery? So we want to construct this filter such that we can reconstruct the original continuous time signal even after sampling. Okay. And this h of j omega is also given to us. So this is a band pass filter with cutoff at omega a and omega b. Okay, plus and minus. So note that we are using band pass filter for reconstruction now and not the low pass filter. Okay. So the question is, can you find appropriate omega A and omega B? This T and A I will explain. T is, yes, the spacing between this train of impulses. A is the magnitude of the bandpass filter. Okay. So we want to find these parameters, period of sampling train, amplitude of the filter, and the cutoff frequencies of the filter, such that the reconstructed signal exactly matches with the original signal. So that is one part, and there is another part also in this question. What is the maximum T you can have such that you get exact recovery? So let us understand the meaning of that question first. So here, yes, we saw that compression in time is sparsification in frequency. Yeah, so having maximum T means how much sparsity you can incorporate in your train of impulses such that you still get exact recovery. Is that we are trying to figure out? Okay, so that's what we mean by finding the maximum T. So in the first step, we will just find some values of A, T, omega A and omega B to get an exact recovery. And in the second step, we will find the maximum possible T which we can have so that we can still get an exact recovery. Alright, so this is also given to us. 2 times omega 1 is strictly bigger than omega 2. So omega 1 and omega 2 are these frequencies. Okay. So this is given in the hypothesis. So we will see how this gets used in solving the problem. So is the question clear to everyone? What we are trying to find? Okay. So first part is easy. That should be easily understandable. So let us see how to get values of these parameters for exact recovery. We won't worry about maximum T or minimum T or whatever. Okay, so let's take Fourier transform of the train of impulses, which is this in the frequency domain. So yeah, we get another impulse train with magnitude 2 pi over T. So we are going to have convolution with this impulse train. Yeah, so x of j omega is going to get convolved with an impulse train, and yeah, you'll get spread out spectrum like this. Okay, so let's suppose that this was the original spectra to start with. So we have 1 over t factor. Then we go from multiplication to convolution, and there is a 1 over 2 pi factor also when we go from multiplication to convolution. So this 2 pi and this 2 pi cancels out, and we are left with 1 over t factor. And then the original spectra, which was these two triangles, which are facing away from one another, they will be spaced like this. So any questions regarding this figure? This is the original spectra. This one is this convolved with the first shifted impulse and so forth. So let's consider this case where this first shifted impulse lies to the right of the original one. Okay. So 2 pi times 2 pi over t, which is omega s, the sampling frequency, and omega s minus omega 2. Okay. So that is strictly bigger than omega 2. So in other words, so 2 pi over t minus omega 2, which is this point, is strictly bigger than omega 2. So 2 pi over t is strictly bigger than twice omega 2. This is Nyquist criteria. And if this is satisfied, then we get this figure, and now we can use a band pass filter with cutoffs as follows. So you take omega A to be between 0 and omega 1. So omega A is between 0 and omega 1. You can choose omega B also appropriately, bigger than omega 2 but less than 2 pi over t minus omega 2. So that's omega B, and A will be t, okay, because there is 1 over t factor here. So when you apply this band pass filter, you are going to get an exact recovery. So any questions on that? This was straightforward. Okay, good. So let's make note of this thing also. So t we took to be like this. So this condition was satisfied. 2 pi over t is strictly bigger than twice omega 2. So pi over t is strictly bigger than omega 2. So in other words, t is strictly less than pi over omega 2. Okay, just rearranging terms here. Pi over omega 2 is strictly bigger than t. Okay, so if t is this one, t is strictly less than this, then you always get an exact recovery. And that is sort of intuitive. So t is, we are making t small here. So we are compressing in time domain. And of course, you compress in time domain, yes, the chances of having exact recovery, of course, increases because small t corresponds to higher sampling rate. And now we want to ask slightly difficult question, but not too difficult. So what is the maximum t that we can have so that we can still recover the original spectrum with bandpass filtering? Okay. So let's try to understand that part. Okay. So as long as this this triangle lies to the right of omega 2, we can always recover using bandpass filtering. And as you start reducing your sampling rate, this lobe starts coming closer and closer to this lobe, this principal lobe. Okay, so as you start increasing t, this lobe starts coming closer and closer, and at some point you are going to have an overlap. Okay, but note that if you still keep increasing t, then this this lobe is going to get transferred more and more to the left of this lobe, and if you choose t such that this lobe lies entirely to the left of this primary lobe. So yeah, this point goes beyond omega 1. Yeah, so maybe I will show it by a picture. Yeah, something like this. So that lobe, this one, which was to the right of this, now comes to the left, and we can still avoid an overlap like this. I will show the picture again. So this lobe, as we start increasing T and start reducing the sampling, comes more and more to the left, and if it entirely comes to the right of, to the left of this principal lobe, we have still avoided overlaps and we can still recover using band pass sampling. But we cannot use low pass filtering in that case. Yeah. So this is that picture. And now if we use low pass filtering like this, then these lobes are going to get picked up, which are going to give us an alias. So low pass filtering won't work in that case, but band pass filtering will work, and you can still avoid an overlap. Okay. So that is the case we want to understand now. Yeah. So in here we took 2 pi over t minus omega 2 to be strictly bigger than omega 2 and use band pass filtering. But low pass filtering also could have worked here. And now we are considering the other case where 2 pi over t minus omega 2 is strictly less than omega 2. So here it was strictly greater and now it is strictly less. So any questions on that? Just go through this on your own also once. It should be clear. Okay, so now let us understand this case when this is exactly 0. Okay, so what I am saying is this point comes exactly at the origin. Yeah. So this is 2 pi over t minus omega 2. We are saying this is 0. So this comes at the origin. This point is 2 pi over t minus omega 1. We want that to the left of omega 1. So this part we want it to be less than omega 1. And, yeah, this is equal to 0. So putting that equal to 0 is same as saying that omega 2 is 2 pi over t, which is what I've written here. So this point, which is the origin, is same as 2 pi over t minus omega 2. This point is 2 pi over t minus omega 1. Okay. And we are going to have this lobe also coming from the other section of the spectrum. And yes, these two lobes are going to meet at this point. Okay. And now, yes, uh, we have to design now a bandpass filter to have an exact recovery. So cutoffs, yes, again, as you can see, you can take omega b to be exactly same as omega 2 since both these lobes are 0 at omega 2. Yeah, with that cutoff, you don't get any overlap. Okay. Omega a, you can choose it between these two. So greater than 2 pi over t minus omega 1 and less than omega 1. Okay, so omega b is omega 2. This is a condition on omega a. So let's rewrite this part. 2 pi over t is same as omega 2. Yeah. So we can write omega 2 in here. And now we are choosing omega b to be same as omega 2. So you can substitute in place of omega 2 also in here. And this is the condition we get. So this top inequality, or even this one, omega 2 minus omega 1 is less than or equal to omega 1, which means omega 2 is strictly less than twice omega 2. This is our given hypothesis. So the reason I am writing strict inequality here is because omega A is strictly greater than this quantity, and omega A is less than or equal to omega 1. Okay? So omega 1 is still strictly bigger than this quantity. And this was the hypothesis, the problem. So we see that coming in here. Had this not been true, then yeah, this filter design might not have been feasible. Okay, so we need this condition. And now with this hypothesis, yes, we can have exact recovery. Okay, and as t increases beyond 2 pi over omega 2, so we had this condition here, omega 2 to be equal to 2 pi over t. You can write that as t is equal to 2 pi over omega 2. If you try to increase t further, then there is going to be an overlap of these lobes. Okay, so this is the maximum t you can get. So this you can check. You can reduce t, okay, until this lobe comes closer and closer to omega 1. So if you reduce t, then this is going to get shifted to the right, and yeah, you can still reduce t until these 2 points are arbitrarily close. Okay. So if you reduce t further, then there is going to be overlap, but after some point, yes, you can keep reducing t until yes, you get that lobe in here completely to the right of this principal lobe. So those are the two cases with bandpass filtering. So yes, when sampling condition is satisfied, of course you can have exact recovery either with low pass or band pass filter in this particular case. But even when the sampling condition is not satisfied, you can get an exact recovery with band pass band pass filtering. So just go through this. This is an example from Oppenheim. It is also there in problem sheets, and so I will wait for questions if there are any. Alright, second problem, yeah, I'm not going to finish today. Slightly longer. So maybe I will just briefly mention about bilinear transformation in maybe 5 minutes or so. And we can continue this tomorrow then. Okay. So the second example I will do tomorrow, and yeah, we will also continue with bilinear transformation. So yeah, in the remaining 5 minutes or so, let me just briefly introduce this part. Okay. So this is used in filter design, going from S domain to Z domain. Okay. So both are complex. In S domain, we write complex numbers in rectangular form, sigma plus j omega. In Z domain, we write them in polar form. So this corresponds to Laplace transform, and this corresponds to Z transform. Yeah. So r times e to the power j omega. Okay. So this bilinear transformation, I don't know, you might have seen this in complex analysis. If not, it's fine. So what it does is following. Okay. So you can go both ways, from this side to this side and vice versa. So going from S domain to Z domain, the transformation is defined by this rational function. So S gets mapped to 1 minus z inverse over 1 plus z inverse. Okay, and going from right to left, z gets mapped to 1 plus s over 1 minus s. Yeah. So both these transformations are given by rational functions, and let's try to understand them pictorially. Okay, so you can verify that yeah, the following happens. So what happens is while going from S to Z, the purely imaginary axis in S domain that gets mapped onto the unit circle. Okay. So in here you can check that if you substitute S is equal to j omega, then 1 plus j omega or 1 minus j omega that has magnitude equal to 1. Yeah. So this purely imaginary axis that gets mapped onto the unit circle, and going from yeah, Z to S, you can check that if you have a unit circle in here, so magnitude of R is 1, you just have e to the power j omega, so 1 minus e to the power minus j omega over 1 plus e to the power minus j omega, that quantity turns out to be purely imaginary. Okay, so unit circle gets mapped onto the purely imaginary axis. Okay, so both these things can be verified by simple algebraic manipulations. One more thing to notice is the following. So the left half plane in S plane, okay, so these vertical lines, yeah, they get mapped inside the unit circle via this bilinear transformation, and the right half plane gets mapped outside the unit circle. Okay, and again vice versa, whatever you have inside in here while going from Z to S gets mapped into the left half plane, and yeah, likewise for whatever lies outside that gets mapped onto the right half plane. Okay, so these are more or less easy checks, requires a bit of algebraic manipulation which yeah, you can do on your. So some simple ones I will just show it to you. So let's substitute Z is equal to unit circle, okay, and see what we get. So like I was saying, yeah, we just substitute for Z, and this is what you have in the numerator and denominator. R is equal to 1, and now you can pull out e to the power minus j omega over 2 from both numerator as well as the denominator. So these two terms cancel, and what you have in the numerator is j times sine omega over 2, and here, downstairs we have cos omega over 2, so j times tan omega over 2, which is purely imaginary. And likewise, if you substitute S is equal to j omega, this is what you get, 1 plus j omega, 1 minus j omega. The magnitudes are the same. Phases are tan inverse of omega. And, yeah, the phase of this is twice of tan inverse of omega. Okay. All right. So why are we doing this? Yeah. So maybe I will get back to this tomorrow. Just we are almost out of time. Let me not get into those details. Why do we need this? But this is required in the filter design. Okay. So usually what one does is one understands filter design in S domain, and if you want to design filters in discrete domain, you use these bilinear transformations to go to continuous time S domain, and in S domain you know how to design. So there is a step-by-step procedure to come up with required specifications for a continuous time filter design. So using these bilinear transformations, you can transform your discrete specifications into continuous specifications, have your filter design in continuous time domain, and then again come back to discrete domain using this bilinear transform. Okay, so that is the idea behind introducing this bilinear transformation and why it is useful and so forth. So we will see a couple of examples of this also maybe tomorrow, and yeah, that will be the end of sampling. Okay, so maybe on Friday I will do a little bit of systems, and yeah, I will also take questions or doubts if there are any. So we will see next week what to do and so forth. Okay, so thank you all for attending. I will wait for questions for a few seconds, but yeah, the class is done.
Sir, when is the exam?
I don't know. I've not heard it officially yet.